So I was just going to, yeah, I was just going to ask you to tell me if there are any questions, but you mentioned already. So if there are any questions, then we can stop and answer them right away before continuing. So thank you everyone for joining the call today. As Hassan introduced, I'm Akem Aristide. I'm originally from Cameroon, and I'm currently a research assistant at India Networks Institute, actually in my last days at India Networks, because next week I'll be transitioning into a new role. And today I'll be talking to you about part of the work that I've been doing during the course of my PhD on implementing machine learning models in network devices to enable high-speed machine learning in programmable networks. So before going into the topic, I would first of all like to talk a little bit about my research institute. So uh, I don't know if my slides are moving. Okay, so we are located in Madrid, in Spain, basically at the heart of Spain, as you can see on the map, which means you can actually reach any city at the different ends of Spain within a few hours of a train ride or within an hour by flying. And of course, being in Spain, you enjoy the very beautiful weather and a lot of football if you're a football fan. And the peculiarity with Indian networks is that although we are located in Spain, it is actually an English-speaking research center. So all the research work that we do is done in English in order to be able to publish our work internationally and present at various venues all over the world. So we have people from various nationalities here, and another advantage of doing your research at Indian Networks, either as a PhD student or even as a professor, is that we are fully focused on research. So you do not have any obligations to take any courses or to teach, and you can focus all your attention on doing research. And actually, I think if you look at our website, you would see the outputs that we've had over the years, which testify to the quality of work that is being done here at India Networks. So in terms of research, we have 13 research groups that are currently active, of which I'm a member of the Networks Data Science Group, where we focus on analyzing large amounts of data that we have from different kinds of network, be it data that we have from mobile network, from which we can reveal patterns in user behaviors, from which we can be able to examine different social events that are happening in different countries and in different environments based off network traffic, and also looking at ways in which we can use data-driven models to be able to optimize the way networks are managed and even the way these networks are designed from scratch. And we have many other groups which target different areas like cybersecurity, those who are in charge of millimeter waves and wireless networks, network economics, a lot of different research areas. So although networking was the main backbone of Indian networks at conception, right now the research is quite diversified to cover every possible area that you could think of that is related to the internet, to data, and to networking in general. So some of the keywords that you would find in our research paper, I just generated this word cloud from some of the descriptions that we have from the groups. So of course, networking is going to be very relevant for the works that we are doing. Mobile systems, machine learning, of course, um, uh, forecasting, AI, and explainability of machine learning and AI in general, computing algorithms, and all of that. So these are some of the words that you would find. So basically, we are covering all these areas, and we are extending with collaborations with other institutions to be able to target other areas as well that might not feature on the word cloud. So currently, there are some open positions at India. We have currently 8 funded PhD positions, so anyone who is interested should check those out. Like I said, you have the advantage that you're doing your PhD fully focusing on research without having to take courses or to teach. Of course, it comes with its advantages and disadvantages, but consider it as an advantage at the moment. And we also have some research engineer positions that are available as well. So if you fancy coming to join us in Madrid to do some interesting things related to networking, AI, cybersecurity, and the internet, please do check those out. Okay, so our talk today, like I said, will be focused on-device machine learning for traffic classification in programmable networks. And we'll structure the talk in four main parts. So we'll first of all have a background where we try to establish the journey from the traditional networking systems that we have up to the current fully programmable networks that we have. Then we will narrow down the scope to focus on-device machine learning, notably in programmable switches. Then we will look at one of the solutions that we've proposed in order to be able to save time. And then we will show a practical application of this proposed solution in a real-world scenario. So traditionally, we had our network composed of switches and routers, as you would find in every networking system, right? But each node had its own control and data plane. So the control plane here, which is basically where you program this particular device or give it the instructions on how to forward traffic. And then the data plane is basically the hardware that is in charge of forwarding the traffic. And traditionally, each device or each node would have its own data plane and control plane, which would enable you to configure that specific device. Of course, you could connect these different control planes to some management server from where you can send individual configurations to each device. But it was specific in the sense that each device had its own control block. And to be able to improve on this architecture, because with this, first of all, there were the limitations that you have to work on each device individually. So to be able to overcome these limitations, we moved towards SDN, where from a centralized controller, you could be able to program or give instructions to numerous devices in the data plane on how to forward traffic using maybe a protocol like OpenFlow, for example. Now, even with OpenFlow, we still had some limitations because to be able to support new protocols, you would have to redesign OpenFlow, for example, to be able to extend it to support more headers and more protocols. And because of this, the ability to innovate in the network was still very limited because you could not deploy custom programs as easily as you would want to. Luckily, in recent times, even these data planes have also become programmable. So we now have programmable switches, which mean that we can program not only the SDN controller, but also the underlying data plane components, meaning that we can say that the entire network is now programmable. So with a programmable controller and a programmable switch. And the advantages of having a programmable switch or a programmable data plane is that in this case, you can tell the data plane component exactly how to program, exactly how to forward packets. And then the controller's job in this case will just be to send basic table entries that will be used to populate the tables that you've defined in the program that is running on the programmable switch. So it's a major breakthrough that happened like, let's say 10 years ago with commercialization of programmable data planes like Intel Tofino from Intel, whereby we are able to actually tell the switches exactly how to program or how to process the packets that are going through them. So moving on from this distinction between traditional networking and the software-defined networking paradigm, we note that the network complexity nowadays is increasing greatly in order to be able to support all the new applications that we have, be it IoT and massive IoT that is coming with billions of interconnected devices, be it things like artificial and or virtual reality or even autonomous vehicles. All of these things bring a large amount of traffic into the network, and this increases the complexity of the network such that to be able to manage it efficiently, we need a lot more automation in network management. And like in every other area of study today, every other research area today, machine learning is playing a very important role in automating network management. And here you have a wide variety of things that you can do in terms of network management with machine learning, be it from traffic classification, which we'll be talking about in this work, to things like intent-based management or security applications, anomaly detection, intrusion detection, or even for things like AI-based network configuration and optimization. So really, machine learning is already doing a lot in terms of automating things in networking and even promises to be able to do more. In the traditional SDN architecture that we saw, where we have a programmable controller and a data plane which you can configure from the control plane. Typically, the machine learning models will be implemented in the control plane because, of course, the control plane is where you can have intelligent servers, and so we would consider it to be smart. Whereas in the data plane, whose main role is just to forward the traffic, you will not have the computation power that you have in control plane servers to be able to implement models. So that's why in the traditional SDN architecture, these models will be running in the control plane. For these models to be able to run in real time, you need some kind of interplane communication. Yes, there's a question?
Before we get to that, we have a question on
Yes,
the Q&A by Izera Pacific. I don't know if Pacific can activate the mic, but I will read it in the meantime.
yes.
In SDN, is hardware devices proprietary to the software protocols?
So I guess it's asking if the hardware devices are proprietary to the software protocols, you mean? It means, I guess.
Yes.
Yeah. Well, I mean, each manufacturer still makes their own devices, but then there is an understanding that there are popular protocols that are available on that are being used in networking. So, for example, OpenFlow. So in the time when SDN was the main thing, where you still had non-programmable switches, most of the switches available could come from so many different vendors, but typically all of them will support protocols like OpenFlow, or some vendors would have their own vendor-specific protocols, but then there will be common protocols that almost all the vendors are going to support. So then it's easy to have a protocol, depending on what controller you have, that can be able to communicate with those devices. So even any vendor could design their own protocol, but then you would have common ones like OpenFlow, which is most popular and which you would find being used in most of the networks around. Yeah.
Thank
Okay.
you. Hope Pacific, your question was answered. Yeah, we'll let Akim continue.
Yeah. If any other thing, you can just follow up in the chat. So like I was saying, to be able to allow the control plane run the machine learning model in real time, we want some communication between the control plane and the data plane, because the data is going through the data plane continuously, and the control plane is trying to run real-time classification on the data that is going through. So the only way it can do this is if it's able to have some kind of real-time communication with the data plane. So this means that there will be some back and forth whereby either you are collecting some samples of the traffic, because possibly you can't send all the traffic to the control plane because you're going to overload the small bandwidth that you have between the control plane and the data plane. So you would generally get samples of the traffic to the control plane, extract features from those samples of traffic, run the machine learning model, make an inference, and then send table entries back into the switch so that it can update the tables that you have in the switch and therefore have new forwarding rules. So this is what you would typically do. However, the control plane, tell me more, sorry. So, however, the control plane is slow in the sense that because you have all these, you are not using an ASIC for in the control plane. You have just some server with a NIC, which is not necessarily as fast as what you would have in a low-level ASIC that you have in the data plane. So control plane operations will typically happen in milliseconds. And so because you have a control plane which is able to run things at about millisecond speeds, and a data plane which can run things at up to nanosecond levels of latency. So it's really rapid because you're using a switching chip that is able to forward those packets directly. Then you're going to introduce a latency which could be up to tens or hundreds of milliseconds when communicating between the user plane, or rather the data plane. I would use those words interchangeably. This latency, therefore, means that you cannot run things at ultra low speeds. So in 5G transport, for example, and going towards 6G, we are talking of being able to do things at less than 1 millisecond. And if you have low latency or ultra low latency applications where you want sub-millisecond latencies and you want to be able to make these decisions within the network, this scenario will not be suitable because then you're inducing latencies which are more than a millisecond. So this is the main thing that we are targeting in this work on on-device machine learning. We want to be able to eliminate this interplane latency, which is of the order of tens or hundreds of milliseconds, and be able to introduce machine learning directly into the data plane components so that we can run machine learning at nanosecond or at most microsecond levels of latency. So that's the main motivation. So another question?
Yeah, this is me now asking. Don't we also have a little bit of communication overhead now? Now that we separate the planes and then the controller is sitting somewhere while the switches are somewhere else. So what about communication overhead?
Yeah. So I mean, in a normal functioning of the network, without you bringing in some additional function, like some additional application, like the in-network machine learning, which we are trying to do here, the bandwidth you have between the data plane and the control plane will typically be enough to sustain normal communication necessities, like sending some samples of traffic, sending some table entries and all of that. So I'll give you an example. For example, with the inter-Tofino switches, you could have up to 33 gigabits per second on this link. Some of them have as low as 10, but imagine having 33 gigabits per second between the control plane and the data plane. So there's really a lot that you can transmit between the planes without suffering from any additional delay based on the latency. But in our case, even if we have 33 gigabits per second, it's not enough, because with the high-speed data planes that we have now, we are talking of terabits per second of traffic. So there is no way we can send all these terabits per second of traffic to the control plane. Okay. So for normal functioning, you have enough resources available between the planes to be able to communicate effectively. But for more demanding tasks, like the machine learning we are talking of, then it becomes more complex if you want to send terabits per second levels of traffic to the control plane. Yeah. Okay. So that's the motivation for why we want to be able to bring these operations fully into the data plane so that we can run them at very high speed, ultra low latency, and at wire speed. Okay. Of course, and this motivation is fueled by the fact that in recent times, over the last decade, we've had the proliferation of several programmable data plane components. So here you have, for example, programmable switches, like this was brought about by Barefoot Networks, which was later accompanied by Intel, Intel Tofino. And you have here a data processing unit, which is basically a special smart network interface card that is also programmable from NVIDIA. You have this smart NIC as well, smart network interface card from Pensando. And this one is an FPGA-based smart network interface card as well. All of these components are all programmable. And depending on where you want to deploy your application, whether closer to the user in the case of network interface cards, or within the network in the case of switches, we now have all these devices that are available and which are programmable with domain-specific languages like P4. So P4 it's a very popular domain-specific language that exists over for probably the last 10 years, since like 2014, I think, which you can use to write code that runs on this hardware. So unlike before, where I would have to just run my terminal and send, when we were doing the networking lab with Cisco switches, send configurations into the switch and all. Here, you can actually write the program from scratch. So the switch comes as a blank black box, and then you can write whatever program you want to implement whatever algorithm you want to implement in the switch. But of course, taking into account the constraints that these devices have, which we're going to mention subsequently. So with the availability of these programmable devices and languages like P4, which you can use to write code for them, there has been a lot of interest in offloading applications from the control plane to the data plane, including machine learning, which is why we're going to be talking about on-device machine learning, which is basically bringing machine learning into devices like the ones we are showing here, switches and smart network interface cards. So if we are able to achieve this, it means that we are going to transform this programmable switch, which we previously labeled as being dumb in quotes, into something that is smart, because it can now run inference on the traffic that is going through it. So instead of just forwarding the traffic, it can actually run some traffic classification model on this traffic, and then forward the traffic according to the decision from the model. And this reduces a lot the delay that you would have had if you had to send these things to the control plane before making an inference decision. So if there's a question, we can take it.
Yeah, we have two questions. Yes, I'll let you go over them.
Yeah. So Pacific says, I suppose there are maybe more than one signal bus in one link, that is control signal and data signal. If devices on the data plane are dumb, how are they addresses? So if you see, I put, when I say dump, I actually dump and smart, I actually put them in quotes to say it's just a way of saying. So I'll break it down further when I say dump and smart. So when I say smart here is because in the control plane, typically you have a server, right? And this server could be as complex as you want. You could have CPUs, GPUs, whatever you want in this server, and you can do as many computations as you want. So I call it smart in this case because I mean, the limits you have there is basically the limits of the server that you bought because you can do a lot of computations, a lot of operations in the control plane without any direct constraints imposed by the network. Okay, so in this sense, it is smart. Now, the data plane is dumb in the sense that there you have a switching chip, which in order to be able to forward traffic at very high speeds, the kinds of operations that this chip can do have been extremely limited. So for example, you would not expect the switching chip to be able to run floating point operations. It's not able to do floating point operations, for example, which is something that you would need if you want to implement some very complex models. You are not able to do so floating point operations, that means divisions and things like that, right? So you can do simple additions. You could do some binary operations. So you could do bit shifts. You could do logical comparisons and things like that. Beyond that, you can't do so much. You can't do some complex multiplication. It won't work simply. So because of that, we are saying it's dumb, not that uh, not that it can't do anything, but it's a relative comparison, okay, with respect to what you can achieve in a control plane server where you have all the possible resources and what you can achieve in a switching chip, which is meant to just forward traffic. Okay. And Thompson says, by moving machine learning to the data plane, how do you account for computational complexity and what strategies are in place to manage resource constraints? Exactly. So that's what we'll be seeing in the rest of the talk. So basically, how do we deploy machine learning into the data plane? This is what you're asking. So I'll say you should just be patient, and if I don't address your concern in the next few slides, then you can come back. Yeah. Okay. So how answering his question exactly, how do we deploy a machine learning model into the data plane device? Which is exactly what he was asking. So with some of the operations, because they are compute intensive and they require you to be able to perform so many different operations, will be done offline or in the control plane, and only the inference will be done in the data plane. So take note, there is no training that's happening in the data plane. The model is going to be prepared and trained completely offline or in the control plane server and then deployed into the data plane, and only inference will happen in the data plane. So take note of this. There's no training in the data plane. So the first phase you begin by, so with your data set, you begin with all the model preparation phases, your feature engineering, you compute all the different features that you need. So typically we have raw packet traces like pickup files because we want to be able to replay the traffic later on through the network devices to be able to do the classification. So we begin with raw pickup files from which you can extract features, no, using tools like T-Shark, which is derived from Wireshark. Then you can compute your features in Python, run feature selection algorithms, and then train the final model. And from the literature, the model that you train could be anything from a tree-based model like a decision tree or a random forest, XGBoost. It could be a neural network or in the binarized form, could be a binarized neural network. And then once you have the model, the core of the work that you do offline is to then translate this model into a program that can run on the data plane hardware. So what we're using in our case, as I mentioned in the previous slide, is a language like P4. So if I have a model, let's take, for example, the example of a tree-based model, This model, at each node, you have certain comparisons that you do, which decide whether you go left or right on the tree. And you continue doing those comparisons until you reach the leaf nodes. So what you're doing is you're just writing a P4 program that implements the equivalent of all of these operations, and that can be implemented in a match and action table that will run on the switch. So this is the process that you do here using a language like P4. Once you have this program, it can then be compiled and deployed in real time on the corresponding networking device. And then when you have traffic flows that come in, if it's a program that has been deployed on a switch, for example, the program will then run the classification model that you've implemented, and then the traffic goes out already classified. Okay. And so we have different approaches that are in the literature, some, for example, using switches, some using switches that are aided by additional devices like FPGAs. So in this case, the traffic comes to the switch extracts features, which it sends to the FPGA, which can run a more complex model, actually like a deep learning model, and then reports back to the switch. It could perform an action based on the classification result and then forwards the traffic. And you could also have similar models implemented on SmartNICs. So in our work, what we focus on is deploying tree-based models in programmable switches. And in the next slides, I'll say why we focus specifically on tree-based models and why we are using switches. So let's start by looking at why we are using switches. So first of all, because the switches are everywhere in the network, so they have an ubiquitous presence in the network. You would find a switch at every part, be it at the access or at the core. So wherever you have a switch, you can potentially have an inference engine if you can implement machine learning on the switches. And also the switches have so many ports. So you could have 32 or 64 high-speed ports on a programmable switch that is available on the market currently. That means that you can have many different channels for different possible inference tasks that you could run on this device. And of course, they offer very high throughput. We're talking of terabits per second speeds, and of course, ultra low latency. So this is a strong motivation for why we want to use switches as opposed to something like NICs, which of course are very good, but of course the NIC is closer to the user. It's installed on some server or some host. So there you want to run inference on traffic that gets only on traffic that gets to that host, not on any other traffic that could be present at any other point in the network. And also things like NICs have very few ports, probably 2 to 4 ports, which do not offer you the luxury of 32 to 64 ports that you have on a switch like this one. So, of course, there are not only advantages on these switches, they have several constraints, just like the question that was asked. So, because these things are supposed to run at very high speed, the number of operations that you can do on each packet are very limited. So for several things, for example, accessing stateful registers in these devices, you can only do that once in the life cycle of a packet. So that's a strong limitation because you cannot implement loops. So if your model involves loops, if you cannot find a workaround for that, you can't possibly implement it. And then we have limited support for mathematical operations, like I mentioned. You can only do basic additions or bit operations. And the amount of memory that is available is low because in these devices, you have expensive memory types like TCAM and SRAM, which are not available in large quantity. So the question then becomes, how can we handle these constraints when deploying models into these devices? And I would say that justifying why we use tree-based models is already one answer to this question because tree-based models are actually simpler, okay? So why are we using tree-based models? It actually answers part of the question. The main reasons are two. The first one is that the structure of the tree is very simple and makes it easy to deploy onto the pipeline of the switch. If you look at the diagram I have here at the bottom, this is a basic tree from the popular Iris dataset that you have for demonstrating basic machine learning classification task. So you see that here, when you start on a root on the root node, depending on the result of the comparison that you do on this feature, you can either go left or right. So basically, you have a condition that you check, and based on the match that you have here, you can perform an action which is either left or right. And that is very much what you have in the switch pipeline of a programmable switch. Typically, you would perform a match, which is basically a comparison that you do between something you extract from the packet and something that you've stored in the tables. And then based on the result of that comparison, you can then execute an action. So because of this analogy, it is very easy, or let's say it is much easier to implement a tree-based model into the switching pipeline compared to a more complex model like a neural network or something. And then the other reason is that for tabular data task, which is the case for most of the traffic classification use cases that we have in networking scenarios, these models are actually on par with or even outperform deep learning models, as you would see in this paper from NeurIPS 2022. So for these two reasons, tree-based models are the favorite for deployment in a switch scenario. So yeah, let's take the question. So he says, I wonder how fast the inferencing will be compared to the basic rule-based approach used in a typical network. So it will be at the same speed. So the idea of deploying a model into the switch is to be able, this is the idea, to be able to achieve machine learning inference at the same speed at which traffic is forwarded. So if you have a problem where you are able to have a rule-based approach, okay, that is as accurate as the machine learning model, then you don't need to train a machine learning model and go through the stress of deploying it. So this is only relevant in cases where the particular inference task that you want to perform is better done with a machine learning model than a normal rule-based approach. Because if you can just implement some simple rules in the switch, then it's fine. You don't need an inference model. But then if this use case needs an inference model, then you implement the inference model in this case to be able to get better accuracy. But for in terms of speed, you get the same speed because as long as you're able to deploy the application in the switch, it's going to run at line rate. So can you please explain again how the trained model is implemented after training and how the P4 programming language comes into play? Okay, yeah, I'll provide a few more details about that in the next slides about how we implement the model. So now I'm justifying why we decide to work with tree-based models and why we're working with switches. And subsequently, I'll provide more details on that. Okay. So, yeah. So in terms of, so a lot of work has already been done in this area of deploying models into switches. Okay, so I want to go into the details of what who has done what and all of that. But the limitations that we have in the existing works are that majority of these works were not designed taking into consideration the constraints of the hardware. Okay, so what happens is basically a model is trained without necessarily taking into consideration the constraints of the hardware, and then later this model is deployed into the switch, and then tweaks are made or workarounds are found to be able to implement the model. But we realize that if you actually take into account the constraints from the start, it actually facilitates the deployment of the model. Also, majority of the solutions that were existing at the time when we started working on these were stateless. So basically per packet classification. And of course, running per packet classification is limited in the sense that you only have basic features that you can extract from the headers of packets. And so you cannot leverage relationships that exist between different packets of flows. And also, majority of the work that was done was not publicly available. So in the works that we proposed, we tried to address these different constraints. So we proposed several solutions where we tried to solve the different problems that we identified, beginning with HENA, which was a solution we provided for stateless inference, whereby we split complex problems into simpler ones that can then be deployed individually into with smaller models that together can yield a more accurate solution compared to a single model that is too complex to be implemented. Then we proposed other solutions for stateful inference like FlowRest, Jewel, and its corresponding use cases. And then recently we had a use case of this work in smart grid attack detection. So in the interest, we'll see how much we can cover, but in the interest of time, we'll focus only on one of the solutions and one use case, and we see how much we can be able to get in the remaining time. Okay. So let's talk about how we achieve flow level inference in switches with random forest. And by a flow here, we are talking of a group of packets with the same 5 tuple, right? So the packets are coming from the same source IP and destination, source IP and source port, and they're going to the same destination IP and port, and they are all packets of the same protocol. And this was, we presented this work at Infocom 2023. So the motivation for this work is that with the packet level approaches, because we are using very simple features, we hardly reach high accuracies because we are not leveraging the intrinsic relationships between the different packets of flows that flow level classification can enable us to have. And also, generally, when you are designing policies for networks, so like somebody asked about rule-based approaches, you would define rules according to groups of packets, not for individual packets. So you would say every packet, for example, that has this source IP and this destination IP should be treated this way. So in that way, you're designing policies for groups of packets, or rather for flows, instead of individual packets. So if you're already designing policies for groups of packets, why not just classify groups of packets? But it turns out that classifying flows is actually quite complex because it requires that you should maintain state in these devices. And considering the limitations that we already mentioned, maintaining state and computing stateful features is the major challenge that we try to address in this work. So in summary, what we do in Flores is that we show that we are able to achieve flow level inference using features that are computed over multiple packets of the same flow. And we demonstrate also in the different use cases that we test that it is more effective in handling difficult inference tasks. And a key thing which we do is that we ensure that the models that we train are natively tailored to the hardware constraints that we have in the switches. So here, for example, I illustrate one of the techniques that we implemented for feature compression. So let's say we have a feature that is 32 bits, and we want to be able to fit this feature into a unit of TCAM for a range match, which is just 20 bits. So what we do is that we design this algorithm where we are able to go through all these different possibilities of the sets of bits that we have on this feature to be able to find what the minimum number of bits and there are different positions that we have in the entire bit string that we could extract and use in place of this feature and still maintain a reasonable accuracy. So with this kind of techniques like this, we show that we can actually tailor the model natively to the constraints of the hardware, and that enables us to have a high accuracy. And we ensure that the solution that we propose is general purpose, so we could adapt it to so many use cases, as I'll show later. And we made it open source, and at the time it was the very first solution that we had that was published implementing stateful inference in programmable switches. So the overview of the system, the way it works, is quite complex. I'll try to go. I won't go through all the details, but if more questions come and we have time, we'll try to answer them. And this should answer the question about how we actually implement the model. So let's assume you know what happens, from when you, like I mentioned before, from when you have the data set until when you train the model, okay? But even before that, there are many steps that we take, okay? So we begin with the hyperparameterization, right? Okay, so to be able to determine whether, if we are deploying a random forest model, we want to know what is the number of estimators that we want to use, what is the maximum depth of the trees, and things like that. So we run grid searches to be able to select all these different parameters. And then once we have those parameters, depending on the data set, we want to also be able to determine how we are going to initialize the stateful registers that we have in the hardware, okay? And to do that, we have a stage where we do this flow management parameterization. So depending on the number of flows that we expect to find in the data set, we can compute the number of register arrays that we would need in order to be able to optimize how we use the memory in the switch. Then once we have the model, we can then convert the model into a P4 program. So I'll pause here 1 minute to explain briefly how that happens. So when you have the model, I take a decision tree, okay? So actually I kept that as a backup slide, but since someone asked, probably I think I'll just go there and explain, because instead of coming back to it. So this is an example of how you could implement a tree into a match and action table that becomes like a rule table basically in the switch. So let's say you have this simple forest, this simple tree with 3 nodes, and you have 2 features, feature A and B. So when you start from the first node, depending on the result of the comparison, if it is true, you go right. If it is false, you go left, okay? So our task with our P4 program is basically to be able to convert this into a table. And we do this by breaking the model down into 2 sets of tables. So we have feature tables and we have code tables. In the feature table, which is basically these ones in blue, you have one for each feature, okay? So for the first feature, A, what you do, you first of all identify the different thresholds of that feature that exist in the model. So for feature A, you have 1 and you have 5. And then you define ranges in between those different thresholds. Okay, so 1 and 5, it means you have 0 to 1. Then beyond 1, which is, so of course, it's in the switch. Like I said, we don't have floating point operations, so we're going to be dealing with only integers and whole numbers here. Then you have 2 to 5, and then beyond 5. Then for feature B, we only have one threshold, which is 3. So you have before 3 and then after 3. Okay, then for each of those ranges that you defined, you're going to assign codes, which are going to be dependent on how you move when you are on the tree. Okay, so if A is greater than 1, you're moving right, which is 1. That is why here it is 1 on the table, basically. And if it is 0, you're going this way, which is 0, which is why you have it here. So in a similar way, you are able to build these tables for all the different features. Now, you have another table where you summarize the combination of codes from the root node to the leaf. So in this case, 0, 0, for example, to get to class 1, which is what you have here. And then 1, 1, for example, to get to class 4, which is what you have here. And the asterisk here are representing the nodes that you don't cross on the path to the particular leaf. So when you get the codes for feature A and the codes for feature B, you concatenate them and it gives you a code word, which you can then match on the code table to get the final class. So at the end, when a packet comes into the switch, what you do is you extract the features, you match them on the individual feature tables. Each feature table gives you a code. Then you combine these codes. It generates a code word, which you can then match on the code table to get the final class. And the work that is done offline to convert the model from a Python model into a P4 program that can run in Switch is basically generating these tables using this simplified algorithm. So yeah, we don't have much time. I could go in more details to explain in more details, but I would continue for the sake of time. So, so basically, this is what happens here. So this is what happens when we talk about P4 encoding here. So you generate this model and you're able to inject that model into your switching program. Then in the data plane, when packets come, you first of all parse those packets, extract the different header fields, check if the packet needs to be classified or not. If it's supposed to be classified, it comes here. If it's not supposed to be classified, it goes out directly. For those that have to be classified, you compute the features, you check if there are hash collisions when managing the different registers. Basically, all the operations that you need for state management. It's a lot of blocks. Each of these blocks can be broken down further, but we don't have time to explain each of them. And then at the end of this phase, you compute the different features for the flow. Note that here we are classifying flows after the first end packet. So you cannot wait because you're trying to do ISP difference. So you can't wait till the entire flow expires before you can classify it. So here, offline in our grid search, we are able to determine after how many packets we have enough information to classify the flow. So sometimes maybe after the first 8 packets, for example, you're already able to classify the flow. And then once you have a classification result, you could notify the controller with a packet digest. And then later, the controller could inject the table entry into the switch to tell it, okay, this flow has already been classified. If you see packets coming from this flow, you don't need to classify them anymore. And then we perform an evaluation with several use cases, comparing it to several benchmarks. I will just flash you with some of the results that we have. If you read the paper, you would find more details. But we show that when compared to stateless solutions, like the motivation, we said that stateless solutions are less accurate. So it's not a surprise here because they use fewer features and they use features that do not exploit the relationship between the different packets of flows. So here we show that Flores is consistently better than all the different stateless solutions that we compared it to. Now, when compared to other stateful solutions, we see that for use cases that are a bit simpler, like this one, the performances are almost the same compared to the other solutions that attempt to deploy this. But for more complex use cases, where we perform actually much better, and we attribute these gains to the different optimizations that we did, including the different hardware model tailoring techniques that we introduced. So we also look, because of course, like I mentioned, we have constraints in terms of resource usage. So we also look at what is the consumption of the different models that we deploy. And you would see that if we look at the most expensive resource, which is basically the ternary match memories that we have, TCAM, you would see that FlowRest is typically among the lowest consumers of this memory type. So we are able to achieve this high accuracy while not increasing by so much the use of TCAM. But of course, if we look at SRAM, we do use more than the stateless solutions, because the stateless solutions, they don't store anything. So they do not necessarily use, they don't use stateful memory because they don't store anything. So because we store a lot of things, to be able to compute stateful features, we use more SRAM, but TCAM is the more expensive one. So being able to optimize for use of TCAM is actually more important in this case. So there's a question before I move to the use case. There is a question. So can you please explain? Yeah, so this is done, I think, because, yeah. And so, yeah, interesting body of work. Just wondering if you have considered incorporating graph neural networks or something related to it. Personally, we've not worked on implementing graph neural networks, but recently, specifically in Infocom 2024, there was a work that was doing neural networks, but not the graph neural networks. Actually, they worked with recurrent neural networks, taking a very simple recurrent neural network and showing that they could be able to decompose the model into and implement one layer of the model per switch. And with this, they were able to achieve a simple deployment of a recurrent neural network. But I've not had a look at graph neural networks, but I'll definitely take a look to see if there's any possibility in that sense. Then Pacific asks if these ML models are intended to optimize like routing path or for other purposes like anomaly detection in the network. So these models could serve for many different things. So the very common one, like in the use cases that I showed here, the use cases that I showed here, so this CIC-IDS is a Canadian Institute for Cybersecurity, and it's an intrusion detection data set, basically. So here we are saying if we are able to train the model to detect if the traffic is malicious or benign. So this is typical intrusion detection use case. And here from University of South Wales, I think this data set is IoT device identification that we do here. So by analyzing the different headers that we have in the packet and computing these features, we can tell from what kind of device this traffic is coming from. And based on that, you can actually do things like QoS optimization, right? So you could say, I have a link with larger capacity here. If you classify this traffic as belonging to real-time video traffic, for example, send it to this specialized link where I have more resources so that the traffic can, go through more easily. So basically, you can have as many possible use cases depending on what exactly you're trying to achieve with the model. Okay. Okay. So um, so I'll take a look at one use case in a few minutes, which is a use case of what we did in Flores. And we presented this work last year at IEEE norms. So what we are trying to achieve here is to be able to get encrypted traffic classification in real time using models trained with Flores. So the motivation here is simply that nowadays, majority of the traffic we have on the internet is encrypted. Actually, as of recently, I think more than 98% of Google traffic is encrypted. And users will typically access these different services through the network, right? So traditionally, we would have some probes in the network that are able to collect different traffic samples and features, and then send them to some machine learning server that could be offline or even completely out of the network to run some inference models, which could then have classification results that could be used to design some policies. So in this scenario, traffic classification is happening completely offline. So it is not in real time as we would want to achieve in the cases that we've mentioned previously. Now, in the traditional SDN architecture, here it's much better because then you're trying to do the classification in real time. But again, because you're doing it in the control plane, there is still the back and forth communication that we have between the user plane or the data plane and the control plane. And in this case, you still have the interplane latency that could be up to hundreds of milliseconds. And so to eliminate this completely, using FlowRest, we propose to deploy the model into a programmable switch in the network so that we can be able to do this classification directly within the network without having to go to any server externally. And so what we do is simply by deploying Flores into this programmable switch to be able to achieve this task as we've described previously in the main paper. So we evaluate this task with an encrypted instant messaging application classification use case, whereby the flow rest enabled switch is able to tell just by examining features based on the packet size and the interarrival time what application this traffic is coming from. So we could be able to distinguish between these 6 applications: WhatsApp, Signal, Telegram, Teams, Discord, and Messenger, with reasonably high accuracy. So I think we were able to get an F1 score of about 0.9 and an accuracy of about 0.89. And in a scenario where you want much higher accuracy, actually you could have some kind of coexistence with a control plane solution. So where in the case for classes where you have lower accuracy, so you could have a threshold, for example, if you're dealing with a class where the accuracy is less than 95, so in this case, these other ones, you could send these classes to the control plane for more classification, of course, sacrificing latency, and such scenarios could enable you to improve performance. And when we look at resource usage, the models that we deployed actually use less than 10% on average of the total resources that we had available on the switch, meaning that we could efficiently implement this encrypted traffic classification use case on the switch using flow rest. And this is a practical application that you can have. So on that note, I would end here and take the remaining questions. So I guess there's one more question from Pacific, and he asked, implementation of these models can get rid of routing protocols like OSPF in network infrastructure. Yes and no. So yes, in the sense that if you want to eliminate the OSPF completely, but you still need what OSPF was doing, if you still need the OSPF functionalities, then you have to write your own program. So you could basically write your own custom version of OSPF. You don't need to implement traditional OSPF. You could write your own custom version and include your own additional functionalities into it. In that case, you don't need the legacy protocol anymore. So in this case, for example, the switches that we have here that we're working with, like I think I had a picture of our test bed here. In these switches, for example, we are not running any legacy protocol like OSPF or whatever. We are just running the programs that we write. So we are doing inference, but then we also have a forwarding program that we implement that can also forward the traffic. So yes, you can implement whatever protocol you want, whatever program you want, as long as it's hardware feasible and is able to compile. Okay, so in the model to action table mapping, what was the asterisk? So the asterisk basically, so when you have ternary matches, no, you do have wildcards where these are values that don't matter. Okay, so you don't care what is the value of these numbers. So for example, if you're going from the root node to class 4, for example, you don't care what is the value of you don't care what will be the result of this comparison. Do you get? So the result of this comparison in that case is an asterisk because you don't care what is going to happen here. So you have 1, 1, and then here you don't care. Whatever is here doesn't matter. Whether it's 0 or 1, it doesn't matter. So that's what the asterisk means. So with ternary matches in the TCAM memory, you can actually implement this to say that if these two conditions are met, whatever is here doesn't matter. It's verified. Okay. Yeah. Okay.
Do
I don't know
you
if
have
there's any other
other
question.
questions? Yeah. Well, comment, Akim. I mean,
Yes.
I remember when I was on the PhD and doing a little bit of network, we were talking and saying, "Oh, is network research dying?" So, but what we are seeing is that in fact we have. I mean, this has revived actually research in networking, and it's. I mean, just wanted to bring that up, and I mean here your thought about it. Looks like that network research has been back.
Yeah. Yeah, I agree with you 100%. And I think um, there over time, I might be wrong, but I also noticed that actually there was less interest in networking, even from my time at CMU. Fewer people were taking the networking courses compared to machine learning courses or cybersecurity courses. But I would say that with network programmability, there is a lot more possibilities that have been opened up, in the networking space. A lot has been unlocked because we are able to, so in-network computing is one thing, right? So we are able to do all these different tasks to show that we can be able to do a lot of computations in the network and itself. So to achieve these things, we need people to come to research in the networking. But away from that, even so, we talk a lot about AI for network. So we're using AI to solve some problem in the networks, but then there is networks for AI as well, which is now becoming very important, and very critical with all the different large language models and all these things you're doing. These programmable switches can also help in things like data aggregation. So if you have different workers that are located in so many different parts of the network, you want to be able to aggregate the different model weights or model parameters that are coming from these places at very high speed. So programmable switches and programmable networking can also help a lot in this phase. So we are going a lot more towards full softwareization, but things will be transformed, but it's still going to be very relevant. So hopefully a lot more people take interest into these things, and yeah, it's going to be interesting to see how it pans out. Also, a lot of vendors are coming in to see how they can bring about more programmable network devices. Something like the Intel Tofino is dying out a little bit because of Intel, but there are other manufacturers that are coming in, and it's also shifting a little bit more towards the user with a lot more programmability on the end host using smart network interface cards. And I think it's exciting to see. There's going to be a lot more that will be possible in this fair.
Wonderful, wonderful. Thank you, Akim. This
Yeah.
is great. We are 2 minutes past the hour. We would like to be mindful of people's time.
Mm.
So maybe this is our time to thank you again for the wonderful work and the great presentation. And yeah, wish you all the best,
Mm.
on
Yeah, yeah,
a couple of things. But
yeah,
yeah, so really great work, uh, good stuff. Thank you very much. And
yeah.
maybe if you can have a round of applause for Akim.
Mm. Yeah, thank you very much. Thank you so much.
Yeah. So thank you for your time, and yeah, we'll be in touch.
Yeah, yeah, thank you very much, and hopefully see you guys soon, sometime in Kigali.
Definitely,
Yeah,
yes, you need to come back home.
yeah, yeah, sure, sure. Okay, thank you
Uh,
very much. Thank you, everyone.
Thank you. Bye-bye.
Yeah, bye.